Hello Sampriti, can you hear me?
Yes, ma'am.
Okay. So today we will start with the organic spectroscopy, and the screen is visible, right?
Yes, ma'am.
Okay. So as we discussed yesterday, we already covered the polymer chemistry chapter. Few of you were not there, so if anyone have any doubt, please when you will join the class, please ask those. Okay, and I'll upload the assignment, so we will discuss that. Okay, so today we are going to start the organic spectroscopy. So, what is basically the spectroscopy mean? The spectroscopy is basically the study of your light matter interaction. So, when light radiation falls on any material, like solid material, which can be crystalline, amorphous, or any kind of material, then what kind of changes were happening because of that interaction? So, the study of that kind of interaction is basically called as a spectroscopy. And basically for characterization of organic spectroscopy, we basically use the three characteristic tool. The first one is infrared spectroscopy. The second one is the UV visible absorption spectroscopy, and third one, which is most commonly used, is your NMR, by which we can characterize the structure of your molecule, which is unknown. Okay, so first we are going to see the infrared spectroscopy. So when we talk about infrared spectroscopy, basically it's also known as vibrational spectroscopy. Okay. So what basically the characteristics of infrared spectroscopy here? The radiation we were using for study of matter is basically infraradiation, and it's mainly used for functional group identification. So, which functional group is present in your molecule? Like, if there is any carbonyl group within that carbonyl group, is it a ester or the carboxylic group or just aldehyde or ketone? So that kind of information we can characterize by using the infrared spectroscopy. And the basic criteria for the molecule for showing the given spectroscopy, that is IR, is basically there should be a dipole moment, induced dipole moment, either induced or permanent dipole moment in your molecule. Then only your molecule can show the IR. It can be IR active. Okay. So when we are talking about the dipole moment of the molecule, for example, let us consider the diatomic molecule like HCl or H2O. In these cases, if we see the geometry of the molecule, or in case of HCl, there will be a particular dipole induced along the axis of your internuclear axis between the HCl, right? So here your mu is not equal to 0. Even in water molecule, there will be a particular dipole moment associated with it. So when there is a radiation falling on the molecule, that is the quanta of photon h nu, then there will be a particular kind of interaction and getting induced within that matter because of the radiation. So that's basically give rise to some kind of changes in the molecule, right? So there will be either there will be a permanent dipole in the molecule. For example, in case of HCl, there will be a visible electronegativity difference present, right? Or even in the water molecule. So there will be a permanent dipole associated with it, but in certain molecule, after the radiation only, the dipole can induced because of the electronic distribution get changed before the radiation and after the radiation. Then even if the such kind of dipole moment is present in your molecule, then also that molecule can be IR active. So this is basically the criteria for your given molecule to be IR active. Okay. This is the main thing. Your mu should not be equal to 0. So if we consider the homonuclear molecules, for example, so H2O, HCl, these are IR active. Okay, so they can be IR active because there is a dipole moment in the molecule. But if we consider the molecule like H2 or Cl2, in those kind of molecule, there will be even after or before the radiation, mu is 0. So there is no any dipole associated with it, right? So if you consider the hydrogen molecule, the both are having a same electronegativity. Also in case of chlorine, even they are electronegative, but both are the symmetrical in nature and symmetry exists in the molecule, and hence the overall dipole is becoming a 0, and hence these molecules are basically IR inactive. So the exception for the IR spectroscopy is this homonuclear diatomic molecule, because they are not having the permanent dipole moment or induced dipole moment, and hence they are IR inactive. So how basically the spectra, infrared spectroscopy, when we are doing on a molecule, how the basically spectra look? Okay, so it looked like this. On y-axis we are measuring intensity of transmittance, and on your x-axis we are plotting the frequency in term of wave number, that is centimeter inverse. So the usual range for the infrared spectroscopy lies between 2.5 to 25 micrometer. So if we convert it in centimeter inverse, that will be, centimeter inverse is basically 1 upon micrometer into 10 raised to 10 raised to 4. Yeah, so then the range will be lying between 4000 to 400 centimeter inverse. So this is the basically range for your infrared wavelength. Okay, and as we know that the energy of your photon is given by h nu, where nu is your frequency of radiation, which can be further, we can write it as hc by lambda. So from this equation, it's easy to understand that the energy of photon is directly proportional to the frequency of radiation and inversely proportional to its wavelength. Okay, and basically the wave number, this 1 upon lambda term, we can also write it in term of a wave number, and hence energy is proportional to a frequency that is directly proportional to your wave number. As you can see that this 4000 is basically in terms of lambda, right? So in terms of frequency, this will be a smaller value. As you can see here, the wavelength 1 upon lambda is basically represented by this wave number, so it's inversely proportional to like the frequency is inversely proportional to lambda value, and the 400 centimeter inverse is basically representing your higher frequency value. In terms of frequency, in terms of wavelength, this one is the higher and this one is the smaller, but in terms of frequency they are basically getting interchanged. So that's the that's how the peak the characteristic peaks we will observe in the IR spectra in the range of 4000 to 400 centimeter inverse. So something it will look like this. Spectra will look like this. So there are particular peaks present in the molecule. We will discuss what, like, there are some characteristic value correspond to which, if the value is that, then we can conclude that the particular functional group is present in your molecule. Okay, so now basically this range of infrared spectroscopy is divided into the two regions. So the IR range that we discussed, 4000 to 400 centimeter inverse, is basically divided into the two regions. The first region is basically called as your fingerprint region, and the second one is called as your functional group region. As you can see that this range 4000 to 400 centimeter inverse is basically a very narrow range, right? And hence there will be a lot of overlapping of peak will be observed. As a result of that, you observe the overlapping of peaks. So that's why only on the basis of IR we can't just characterize the molecule. That's why we have to use the UV visible spectroscopy, either UV visible or the mostly trustable is your NMR spectroscopy we use in the laboratory to determine any unknown molecule is given to you. Then we use basically NMR, mostly NMR is used, and then we move on toward the IR or the UV visible spectri for the further micro determinations present in the molecule. Okay, yeah, so we were discussing that there are basically two regions, fingerprint region and the functional group region. Basically the fingerprint region lies in the value 500 to 1500 centimeter inverse, and functional group region corresponds to the wavelength range of 1500 to 4000 centimeter inverse. So basically in the fingerprint region we will observe the bending modes of vibrations. So as we discussed, as in the introduction I told you, when we are talking about IR spectroscopy, basically we were studying how the radiation changes the vibrational pattern or vibrational motion present in your molecule. Okay, so as we know the criteria for IR, as we discussed, it's basically the induced dipole moment or the dipole moment associated in the molecule after you are radiating a certain quanta of energy on molecule, right? So because of that there will be the vibrational motion changes happening in the molecule. So we basically study those, what are the changes happening in the vibration motion of molecule, and corresponding spectra we will detect from the detector, right? So in the region of 500 to 1500 centimeter inverse, this region is basically related to the bending modes of vibration. So we will study later that what are the different modes of vibration, but just for right now remember that this region is corresponds to the bending mode. Similarly, when we are talking about the functional group region, basically the vibrations motion present in the molecule here are representing stretching vibration in that region. Okay, so stretching vibrations are present in the functional group region. So this is basically the classification of the range of wavelength range in your IR spectra. So let us consider, for example, if we have any primary alcohol, and similarly we are having the just structural isomer of that. So only difference is that this is a primary alcohol and the second one is the secondary alcohol, right? So if you observe the IR spectra of both, you will notice that the stretching frequency of both of the molecules will come around 3200 to 3300 or 400 centimeter inverse. So in this region basically you will observe the stretching frequency of both of the molecules. So basically what we will observe here, we are observing the COH stretching frequency, right? So this CO bond stretching frequency in both of the molecule, even in primary alcohol or even in the secondary alcohol, will be the similar. So because this is the similar bond, that is a CO bond, and we are basically detecting the corresponding stretching frequency of that bond. So we can't just distinguish between these two molecules, the primary and the secondary isomers, when we are looking at fingerprint region. Okay, so we can't distinguish by this functional group region. So for that we have to look at other region wavelength range, that is basically by using fingerprint region. So if we use fingerprint region now, then we can characterize the separation by bending region. Okay, so bending will be the different in both of them because the geometry itself or the bond angles will be different, right? So the bending motion in the molecule will be differentiated or distinguished between those two molecules. Therefore we can separate the molecule by using the fingerprint region, that is separation by using the bending region, and hence we can characterize these two molecules. So if you look in the functional group region, they will be almost similar, okay, or almost they will be identical, not even a similar, they will be mostly identical, both the molecule primary and secondary alcohol, because here what we are just analyzing, we are just analyzing the stretching frequency of a CO bond. But when we are talking about a fingerprint region, we are and that's why it's called a fingerprint. Okay, so fingerprint means it's very unique and very precise for that particular molecule, whatever molecule you are considering. Even there will be different isomers present in that molecule, but whatever isomer specific you are considering, it's like a fingerprint of that particular unit you are considering, and that's why we can distinguish by using the fingerprint region or a bending region in that molecule. Okay, so you have any doubt till here? Understood?
Yes, ma'am.
No, for bending vibration, is it how the bond angle changes?
Can you repeat?
For bending vibration, is it like based on the bond angle?
Yeah, it will be the like the vibrational motion will be there, right? So because of the whatever vibrations were happening due to the change in bond angle, that will be corresponds to the bending part. Okay, variation in the angle of bond and variation in the bond distance after the radiation is happening, that corresponds to a stretching mode. Okay, so I'll discuss the vibration modes in 5 minutes. Okay, then you will be more clear about it.
Yes.
Okay, so for example, we are considering the molecule as AB. Okay, so there will be what is basically happening when we are characterizing, what's the process behind it, is there will be a change in dipole is happening, right? So your dipole moment is not zero. So because of this change in dipole, when there is a radiation happening on your molecule, then it basically generates, because of the vibrational motion, it basically generate the electric field component. Okay, because the electron distribution or electron cloud will be changed, right? So that is a motion of the charge that basically give rise to the electric field. And whatever IR you are using, as you know that when we are talking about the IR or particular wave having the frequency h nu, it has a two components in it, right? So there will be the electric field component as well as the magnetic field component, and both of them are orthogonal to each other, and that is also orthogonal to your propagation of your wave, right? So that we have studied in physics, right? Like what is basically when you're talking about the electromagnetic wave, what it has basically the electric field component, magnetic field component, which are orthogonal to each other, and that is basically perpendicular to a direction of your propagation. So basically when we are radiating this energy or the electromagnetic wave, basically it also has corresponding electric field component present in that wave, right? So that also have the electric field component, that is IR, whatever radiation you are using, infra radiation you are using, that also has the electric field component present in that wave. So basically these two electric field, like when there is a change or induced dipole moment, and that basically give rise to the electric field component in present in your chemical molecule. And because of the electromagnetic wave has its own electric field component, so when these both two couple or resonate with each other, then that corresponding frequency is basically giving you the infrared radiation or the absorption will take place. Okay, so this is the mechanism how basically the IR works. Okay, so basically the electric field component of your chemical molecule and the radiation, they when they will couple or resonate with each other, that basically give rise to the IR absorption. Okay, so that's why we say that the change in your dipole moment will result in generation of electric field component, and that corresponds to the radiation which has electric field of a certain frequency, and that give rise to your absorption. Okay, so this is how your IR works. So that's basically the mechanism behind the IR spectroscopy. So now let you have that question, right? The vibration mode. We will discuss that. So when we are talking about the different vibration mode present in the molecule, there are basically a two type of vibrations in the molecule. The first one is the stretching vibration, and the second one is basically called as your bending vibration. Okay, so what does basically a stretching mean? Stretching is basically if there is a change or variation in a bond distance or bond length as we say, then corresponding mode of vibration is called a stretching vibration. And if there is a change or variation in angle of bond, that is the bond angle, then such kind of vibration mode is known as a bending vibration. So now it's clear. Chandana, who asked, I forgot, what's the difference between stretching and the bending vibration mode?
Yes, Makhi.
Yeah.
Yes, ma'am.
Okay, so further the stretching vibrations can be classified into symmetric stretching and asymmetric stretching mode. So what is stretching mode means? For example, as we say that there will be variation in bond distance, right? So let us consider the molecule B2A, and if there is a vibration results into the result into the variation in bond length symmetrically, then it's called a symmetric stretching. And if we consider due to the variation in bond distance is basically asymmetrical in nature, then the corresponding stretching is your asymmetric stretching. Okay. Similarly, when we are talking about bending, there are two types of bending. The first one is your out of plane bending, and the second one is in plane bending. So out of plane bending means how the motion is happening. Basically, it's also called as wagging motion or the twisting motion in the molecule. So let us consider the example of your CH4 molecule. Okay. So if these two are coming like out of the plane, like if we fix the bond that is coming to in like what we say the wedge band and the dash bond, if we fix them, and if the other two hydrogens are doing coming out of the plane, then the corresponding motion is called as your wagging motion. Whereas when you are talking about a twisting of the molecule, is basically this is your plane of molecule, then one hydrogen is coming towards you and one is going back, then such kind of motion is called as the twisting motion. So both the wagging and twisting kind of vibration are giving rise to the out of plane bending. Okay. Whereas when we are talking about in plane bending, it can be a rocking and scissoring. So how it looks, and in case of scissoring, so this is a in plane bending. Okay. So then rocking and scissoring, this kind of vibrations will give rise to the in plane bending. So there are basically a different based on how the molecule is giving the variation in the bond length or a bond angle. There are different classifications were done in different criterias, like in symmetric stretching and asymmetric stretching, that you can easily understand based on how the bond length is varying symmetrically or asymmetrically. In case of bending, as we discussed, it can be the bending motion can give rise to the in plane bending or out of plane bending, and within that how basically the motion is happening, based on that different names were given. Like in case of wagging, both of the hydrogen were doing the variation in the bond angle, or give rise to the variation in bond angle by doing the motion in the in the one direction but out of plane. Then twisting, it is a similar one is like just it is just a twisting, you can play with your two fingers, just take your two fingers and do this all kind of what we say the motions, then you will understand how these motions were happening. Okay. In twisting, one is coming out and one is going in the plane, so then that kind of motion is called as twisting. In case of rocking, is basically both, all the motion whatever is happening because of the radiation is in the plane. Then if both the hydrogens were doing the motion in the same direction in plane, then it is called as rocking. And scissoring means both are hydrogen approaching towards each other or facing towards each other and doing vibrations in that direction due to the radiation. Then that variation in the bond angle is called as your scissoring bending mode. So you understood all the vibrational modes that we discussed. Any doubt here?
No, no.
Okay. So then we will move forward. So just the point to note down: the molecule containing two or more identical atom gives the two peaks. So basically, one will be the symmetric and other will be asymmetric. So remember that mostly when we are doing the spectroscopy in lab, basically we look into the vibrational, like the stretching vibration mode first. If we are not able to characterize, like as we discussed in the case of primary and secondary alcohol, right, before previously. So if we want the very minute information regarding molecule, or we are not able to differentiate the molecule or guess what can be the structure of molecule based on stretching vibration, then only we will move toward the bending region. Okay, so mostly in labs we first see the region of a stretching vibration, and then we need a more further minute information regarding your molecule, then we see the bending region. So that's why here they are telling that when the molecule contain two or more similar atom, basically it's we are talking about the stretching frequency here, and that gives the two peaks. One will be symmetric and one will be the asymmetric. For example, we talk about the different amine molecule, right? So if there is NH2 group present in your molecule, primary amine or any secondary tertiary amine, so in that case here you can see that the both atoms which are constituting this particular bond, nitrogen and hydrogen, will be same in both, in bond A, suppose this is bond A, and in bond B. So here both the atoms were same or similar, but because of there will be two kind of different stretching can happen in the molecule. So one can be like the stretching is basically happening in the similar way, or symmetric stretching is happening, and in other case the stretching will be asymmetric in nature. So corresponding stretching frequencies will be vary from the value correspond to each other. Okay, so basically the symmetric stretching will comes around 3300, whereas the asymmetric stretching value comes around 3400. So generally remember that your asymmetric stretching value is, there will be some exceptions, but in most of the cases you will observe that the asymmetric stretching value will be always greater than the symmetric stretching value. Okay, in usually you will observe this characteristic between the stretching frequencies. Or even in case of NH2, or even you have some nitro group present in the molecule, for example, in that case also you will get two peaks here, as this both the or like the nitro structure you already know, right? So there will be a resonance between bond, right? So that's why there will be this, both the bonds are like almost equivalent with each other. So here also you will get the two peaks. One will be having a symmetric stretching frequency, and the value will be almost around 1000 1350 centimeter inverse, whereas in case of asymmetric stretching the value is little higher, that is 1000 550 centimeter inverse. Okay, so in this way you will observe the phenomenon when you are having, when the atom is atom is attached to the identical different atom, I mean the nitrogen is attached here to the both similar atoms, right, the oxygen, or when your molecule contain two or more identical atoms. Other example is basically anhydride. So for example, if we consider, then in that case also you will observe the two peaks. One is symmetric, other will be asymmetric in nature, and corresponding values will be around 1760 and 1780 centimeter. So these are just example I'm showing you, like how even you are having identical atom in a molecule, it basically give rise to two peaks because of the variation in the stretching. Okay, so this is just regarding the introduction of IR spectra. Now we will move forward towards what are the factors basically which are affecting this stretching frequency. So this stretching frequency is basically given by the formula 1 upon 2 pi c into root of k by mu, where here k is representing your force constant, and basically it's force constant means it's corresponding to your bond strength, how strong or weak is your bond, and the mu is basically called as reduced mass, and it's given by, I think you know, mu is basically m1 m2 upon m1 plus m2. To calculate reduced mass, this is the formula we use. So the first factor is affecting is basically your bond strength. From formula itself you can see that, right, the stretching frequency is correlated with your force constant and the reduced mass. So bond strength means what? Your stretching frequency is directly proportional to your force constant. So higher the value of force constant means your stronger is the bond, then the energy required or the frequency required to induce the variation in that bond length or the bond angle will be the higher. So therefore higher the force constant, higher will be your stretching frequency. So if we consider the example of triply bonded any molecule, the molecule containing a triple bond versus double bond versus the single bond. So as you know that the triple bond will be the stronger, right? The bond length will be the less, and the bond angle will be higher, or in other way we say the bond strength will be the higher, right? So this carbon is basically sp hybridized, sp2 hybridized carbon, and sp3 hybridized carbon. So corresponding stretching frequency values, if we see, the triple bond will be almost around 2150 centimeter inverse, doubly bonded carbon will be around 1650, whereas a single bond will give you the frequency around the 1200 to 1100. Okay, so that's the conclusion we can get by just by seeing the formula. So higher the force constant, higher will be your stretching frequency. And also note that between your stretching and the bending, stretching frequency has the higher value than the bending. This way you can directly, as we already discussed, right? So stretching means we are basically considering a functional group region, and that basically comes in the region of 500 to 1500 centimeter inverse. Okay, means it is having higher frequency, right? So basically this comes in the functional group region that we discussed, 500 to 1500 centimeter inverse region, whereas this will come around 1500 to 4000 centimeter inverse. So this is in terms of wavelength we are talking, and we know that wavelength is inversely proportional to frequency. It means this is having higher frequency and bending region is having the lower frequency. Okay, so this is also like just keep in mind there can be the you can easily in MCQ while solving, if they ask within stretching and bending mode, the stretching frequency will be usually having a higher value than your bending frequency. Okay, now let us consider the second factor. First we talk about the bond strength, and from the formula itself, as we discussed, the reduced mass can also affect your stretching frequency. So stretching frequency is basically inversely proportional to your reduced mass, right? From the formula. So let us consider example as, let's consider carbon chlorine, carbon bromine and carbon iodine. So as you know that if we consider the halo group, fluorine, chlorine, bromine, etc., iodine, then down the group you know that the mass will increase. So basically reduced mass is increasing down the group. Okay, so the we know that if we talk about reduced mass, the reduced mass of carbon chloride bond will be less than carbon bromine, less than carbon iodine, as itself carbon is same or constant within all the bonds that we are considering, only the halo atom is changing. So the stretching frequency, if we talk about the stretching frequency, then from the formula we can conclude this test. No need to remember the value, just understand the how basically order is changing, okay, or how the factors are affecting. So if you even don't remember these values, absolute values, mathematical absolute figures, that's completely fine. Just understand the concept basically, like how if we are talking about reduced mass, down the group reduced mass will increase, and hence basically the corresponding stretching frequency will decrease down the group, down the depending upon what atom is attached. Okay, so this is how the trend of stretching frequency will get affected by your reduced mass. Or you can just also if you see the concept, if there is a heavy atom attached to your molecule, means its reduced mass is high, so it almost do a less vibration. Or what does it mean? It means basically there will be the less electric component field generated in the chemical structure, which can resonate with your IR electric field of IR radiation, and hence your stretching frequency will be less. So both the way you can remember, just like imagine that if there is a heavy atom in your bond, then for varying that, if you are providing the same stretching frequency to the lighter atom and the same toward the heavier atom, if there is a heavier atom, then the vibrational motion itself will be the less. You require more force or the more energy you need to provide for the same value of the vibration which can induce in lighter and heavier one, right? So if we are providing the same energy, then the lighter one of course will give you the higher vibration motion, whereas heavier one will give you the less vibrational motion. And as we discussed, basically what's happening when we are putting the radiation on a molecule, basically there is some kind of electric component field will be generated, and that basically resonate with your radiation electric field. So as in heavier one, vibration is less, which means that the electric field component is less, and which means your corresponding stretching frequency value will be going to affect, it will be less. Okay, yeah. Then so these are the two factors from the formula that you can directly conclude how the stretching frequency get affected by your bond strength and the reduced mass. Now the third factor is basically a resonance. So let us consider, and mostly it is observed in the molecules containing the carbonyl group or conjugated chain. So as you can see that, so here delta minus and delta plus charge separation can be done because of a resonance, right? So basically when you are talking about a C double bond O character, because of resonance there will be a more single bond character will increase between the CO bond, right? So initially before the radiation, if there is no any resonance, conjugated resonance is not there, in that case basically it's completely just a CO bond, right? So it's completely sp2 hybridized, means and we already discussed that how basically a force constant affect the stretching frequency. But when there is specifically a conjugated resonance can happen in your molecule, like alpha beta unsaturated molecule is present next to a carbonyl group, then in that case corresponding charge separation can give rise to increased single bond character of that particular carbonyl group or a CO bond. So it's more like between sp and sp2 now, and that's why its corresponding stretching frequency will vary or it will decrease, whereas here it's pure sp2 and hence the stretching frequency will be higher. So this is how basically your um, resonance will affect the stretching frequency. So if you see the mathematical absolute values, then this will come around 17-15 centimeter inverse, whereas in case of alpha beta unsaturated ketone molecule it will come around 1675 centimeter inverse. So there is a like visible change that you can observe and detect that is your carbonyl group containing molecule it's saturated or it's alpha beta unsaturated, or there is no any double bond conjugation next to it. Okay, so this is how you can also um, determine the your structural characteristics. Now the next factor is basically hydrogen bonding. So how basically hydrogen bonding affects your IR spectra? For example, basically we are talking about a stretching frequency and the force constant here. So if the hydrogen bond is present, so there will be two types of hydrogen bonding, right? So there can be intramolecular hydrogen bond or there can be intermolecular hydrogen bond present in your molecule. If there is intramolecular hydrogen bonding, means it is internal effect, right? So even if you increase or decrease the concentration of the particular molecule in your solution or corresponding system, it's not going to affect. So intramolecular hydrogen bond is basically the internal effect, and that's why it does not get affected or does not changes with concentration or dilution. So either you are concentrating your system or diluting your system, that's not going to affect. But whereas on other hand, in case of intermolecular hydrogen bonding, it's not an internal effect, right? So it depends upon the concentration. So as if you are having a two molecules present in your system, for example OH is there and the other molecule like some NH2 is present. So now if the hydrogen bonding is happening in your molecule, so it depends upon these two components, right? A and B, right? So in that case particularly it depends upon the concentration. So at low concentration or the dilution, the effect of hydrogen bond will basically decrease. Okay, so if there is a hydrogen bonding present in the system, in any particular system, then the stretching frequency of this OH will get particularly get affected. It basically decreases, the force constant here is decreases, and as we see, if force constant will decrease, then corresponding your stretching frequency will decrease as the bond strength will decrease because of hydrogen bonding. So basically hydrogen bonding is affecting the bond strength of the molecule, and hence the specific bond that we are seeing, that bond strength will get affected, and hence the corresponding stretching frequency value will also get affected. So as we discussed, there will be two type of effects shown by hydrogen bonding, intramolecular one and the intermolecular one. So in intra there is internal effect, so sorry. So it does not depend upon the concentration, either you are increasing the concentration or decreasing it or doing a dilution of your system. But when we talk about intermolecular, as we see that if we decrease one of the component, then it going to affect the affinity of the hydrogen bond, right? And hence it affect the bond strength, and hence it affects the stretching frequency. So in this way the hydrogen bonding is indirectly affecting your stretching frequency value. So you understood all the factors that we discussed, how they are going to affect your system. Any doubt here in any understanding, like how the stretching frequency will vary on this different factor?
Clear, ma'am.
It's clear, right?
Yes, ma'am.
Okay.
Yes, yes.
Okay. So now we will move forward. So like keep these factors in mind. Okay, so will see some PYQ or some questions in which we are basically using the same concepts, like how the force constant, then your reduced mass, also the resonance is going to affect your stretching frequency value, and also the hydrogen bonding. Okay, so now we will move forward. Basically there is IR chart we have to remember, so we'll first discuss that. So let us consider IR stretching. So mark it as important. So whenever you are going to revise this chapter, just once see this chart and try to keep these values on your fingertip. Okay, so that will be help you to solve the PYQs, or it's also even when you will further go into a research and when you are doing some analysis of the molecule, then it's easy to, if you remember these values, then you can easily detect or you can easily guess like what kind of different functional group your unknown molecule have. Even you know the structure of the molecule, or you are not there will be some impurities present or not. So by just seeing the IR spectra you can guess that, okay, yeah, so if there is a peak at 300 means there is a saturated molecule or CH bond is present, or if there is a carbonyl frequency means there is a Fermi resonance present in a molecule, right? So like that you can able to guess. So we will see some stretching, like the bond and their corresponding stretching frequency values. So here what bond we are considering and the stretching frequency value corresponding to it. Okay, and like when you will revise 2 3 times, like you will able to memorize it. Okay, so first one is like the CH stretching. CH stretching, which is like sp3 saturated molecule is there, then corresponding stretching frequency will come in the region of 3000 centimeter inverse. If you are talking about sp2 hybridized CH bond, then the corresponding stretching frequency comes in the region of 3100. So we discussed, right? So if as the S character is increasing, the bond strength will increase, and hence the corresponding value, a stretching frequency value, will always also increase, right? If we are talking here, then it will be higher than this, right? So that will be around 3300 centimeter inverse. So just like Sampriti Chandana, just remember that, like even if you give the topic as organic spectroscopy or others also in your interview, then they can just ask this basic question. As you know that in the saturated, or you are just considering the CH bond, the sp2 hybridized CH bond and sp3 hybridized CH bond, how it's basically affecting your stretching frequency. So you have to explain here that, as we can see that here S character is going to increase, means basically electronegative character is increasing between this carbon and hydrogen, right? So with increase in S character, basically there will be increase in the bond strength, and hence there will be increase in your force constant, that is K, and that's how it affected the stretching frequency. Okay, so like that they can ask the questions in interview for exam it's also important, but also remember like also clear your concept, like when you are talking about like when we are going from sp3 to sorry, I wrote wrong here. Yeah, so when you are going from sp3 sp2 and sp character, we are basically comparing what is basically happening and how the percentage of s character increase is correlated with the increase in stretching frequency. You should able to explain this, okay? So they can just ask you what are the values and like explain like why it's happening, just like that. Understood?
Yes, ma'am.
Yes, ma'am.
Yeah, so like don't like worry about like what kind of question they will ask. Just like whatever you have studied is more than enough, but you have to know the basic concepts, like if something is happening, why it's happening, what's its origin, okay? So next we'll discuss CC stretching. So similarly, similarly we discuss the CH stretching. Similarly, there will be CC stretching bond train we can observe. In sp3 hybridized, the value will come around 1000 to 1100. In case of sp2 hybridized, it will be around 1650, whereas when it's triple bonded like the sp hybridized, the value will come around 2150. So you can here also you can see, right, as there will be increase in percentage of s character, here we also observe that the stretching frequency value is increasing, right? So next is basically, yeah, similarly in case of the cyno compounds, the value will be around 2 to 50. So here you can also see with increasing electronegativity, the value there will be increase in bond strength, and hence it's increasing a stretching frequency value. When we talk about the C double bond C in aromatic case, so this is the general case in case of your linear molecule, like linear molecules are present when you are talking about ethylene molecule or propylene, etc. But when we are talking about the aromatic system like benzene ring or the benzene derivative, in that case specifically the value will come around 1600. Okay, so as here all the bond are equivalent in nature, so it's not basically, when we talk about benzene ring, we write its resonance structure like this, right? We write its resonance structure like this, so it's not, it's like a partial double bond single bond character is present here, and hence value is decreasing. So see how minute details are here. Like when you're talking about just a linear unsaturated system, the value difference, you can see the value is basically 1650. But when you are talking about aromatic system, the same bond we are talking C double bond C, but there will be a change in value. So they can just ask why this like if they ask you what is the stretching frequency for the linear unsaturated molecule, like draw the structure of ethene and also draw the structure of benzene ring, and tell now like why there will be the difference in C double bond C like C double bond C stretching frequency. So why it's there, because when you're talking about linear system, it's like pure sp2 hybridized system is present. But when you're talking about aromatic, we already know that we draw the because it's having a resonance in the molecule, right? So this double bond and single bond are basically in resonance with each other. So we can say that this is almost like the bond length is between sp and the sp3 and sp2. So it's like partial double bond character, and that's why its value is getting decreased from the 50 units. Okay, understood?
Yes, ma'am.
Yes, ma'am.
Okay, so next is basically the most characteristic molecule, like mostly in organic, whenever you will do reaction, you will handle the compound containing carbonyl group, or like and its derivative like aldehyde, ester, carboxylic acid, anhydrides, etc. So basically this CH bond, aldehydic CH, gives you a special kind of structure in your IR spectra, and that's basically called as a Fermi resonance. We'll discuss what is Fermi resonance, but yeah, it's called Fermi resonance, and its value will come around 2700 to 2800, or 2800 to 2900. So basically, during this range of frequency, that is between 2700 to 2900, you will observe the characteristic duplet. Okay, a doublet you will observe here. What is it we will discuss, and that corresponding process is called as a Fermi resonance process. So this is just a important characteristic when you are analyzing the aldehydic compound, okay, or the compound containing the aldehydic CH bond. Then we observe in IR spectra there is a Fermi resonance phenomenon happening, and the corresponding stretching frequency lie in the region of 2700 to 2900. Okay, just keep this point in mind. Then next, when we are talking about the compounds, like if there is ether compound, then that also gives the value around 1100 centimeter inverse. And I think I told you about NO2 compound. It basically, as we discussed, there are similar atoms, but there will be more, two peaks will be there. One will be corresponding to a symmetric stretching, other will be asymmetric stretching. So that values will be 1350 and 1550 or 1650, around that they will give the two peaks. Okay, so these are some of the uh, characteristic bond and their corresponding stretching frequency value. Now when we are talking about the CO stretching, particularly the compound containing carbonyl group, so there are so many PYQ just based on this carbonyl containing compound and its derivative. How the they will just ask the order, give the either they will give a structure or give the just name of your chemical compound containing this carbonyl group, and ask you the trend of how the stretching frequency is varying. So when we talk about the carbonyl containing compound, it can be the acid, like if there is a carboxylic group present in the molecule, then the corresponding stretching frequency here will be lie in the region of 1700 to 1725 centimeter inverse. When we are talking about the ketone containing C double bond O and any alkyl chain is present, like, then the corresponding value will be in the region of 1715 centimeter inverse. When we talk about aldehyde, then that C double bond O here is giving you the stretching frequency around 1725 centimeter inverse. Now moving towards the ester, it gives the value around 1735 to 1750 centimeter inverse. And when we talk about anhydrides, then in that case the value will be around 1760 to 1780 centimeter inverse. Similarly, if there is acid chloride present, acyl group like C double bond R, C double bond O Cl, then it has the value around 1800 centimeter inverse. Now if you increase the electronegativity by just changing chloride by fluorine, then the corresponding stretching frequency will increase, right? So that will come around 1817 centimeter inverse. And when we talk about amides, that is basically C double bond O NH2, here also there will be two similar atoms and they gives the two peaks. It will be in the region 1650 to 1680 centimeter inverse. Okay, so this is basically a train between the different carbonyl containing compound. So why basically it's happening, so when we are talking about the acid molecule, it can undergo, like, see, if there is an acid molecule present in your system like C double bond OH, then you can directly see that there can be the hydrogen bond can happen, right? So hydrogen bonding can affect your stretching frequency value, and hence, as you know that the acid is a strong group, but because of the hydrogen bonding, it's basically affecting a stretching frequency here. So in interview they can also ask like this, if they are discussing the question regarding organic spectroscopy, they will just ask you to tell rough value, and you don't need to be very absolute or absolute mathematical figures. You even if you don't able to tell, that's fine, but the range, in what range the acid group will give you the value, in what range ester will give you the value, and just discuss why why it's happening, or why there is a difference in the stretching frequency, and how they are and what factors are affecting it, and why this value is coming. Okay, so in case of acid, why the value is less, because there, because of a hydrogen bonding. Okay, so hydrogen bonding affects your bond strength, that we were discussing here, and that's why it's affect your stretching frequency. When we are talking about the ketone and aldehyde, as you can see that there will be the inductive effect that's going to affect your C double bond. So electrophilicity of your aldehydic carbonyl, the carbon aldehydic carbon is greater than your ketone. That's why the C double bond stretching frequency for aldehyde will be in having a higher value than your ketone value. So these are very small concept that you have learned in your general organic chemistry, like in your GOC. So see that the electrophilicity of your aldehydic carbon is greater than ketone, and that's why it basically affects the bond strength or force constant, and that basically give rise to the higher stretching frequency of your aldehyde. Okay, so these are just a small concept you have to correlate with your force constant or bond strength, and just based on that you can conclude the stretching frequency, how it's varying. Now when we talk about the ester molecule, I forgot to write the structure. So here it's basically C double bond OR, right? So when we are analyzing the molecule aldehyde and ester, so why, when we are talking about this group, so this double bond C double bond is also very within that particular time span in which we are just detecting or doing the IR spectra, it's basically undetectable like which bond is double bond and which bond is single bond. So they are just almost like resonating structure we can consider, where this can be single bond and this can be double bond. So it basically treated as there are two carbon is attached to the two oxygen, and there is a partial double bond between both of them, and hence esters were also having the higher value as compared to your aldehyde. Okay, so like why the aldehyde, if they just ask, they can just ask you why aldehyde and ester, when you are comparing, why the value is getting higher in case of ester, because we discussed early, right? If there is if there is a conjugation present in a molecule, then that can also decrease the value, but here it's not only a conjugation, this oxygen also has its lone pair, right? So it's more or less like both the oxygens are having a double bond. The instrument can't just detect which is in ester, which is your carbonyl group, and which is your OR group, that is here, right, the functional group. So that's why it basically treat it as more like it's like a lone pair is present on this oxygen, and this is having a complete sp2 character, and that's why it's not going to affect the stretching frequency, and hence ester is going to have the higher stretching frequency as compared to aldehyde. And as you know that anhydride it already having a more than one carbonyl group, so that's why it's having the higher stretching frequency. And here also it's clear that with increasing electronegative atom, this carbonyl carbon is again becoming more and more electrophilic in nature, means this bond, the C double bond O, is basically having a high bond strength, and hence the corresponding values are also higher. Okay, and in case of amine or amide group, here now see that this amine can also it's basically reducing the double bond character here. Okay, so when we are talking about amide and ester, they can also ask you between the amide and ester how what is basically difference, and how it's going to affect your stretching frequency. So when we are talking about the amides here it's complete like a resonating structure. So like we discussed the alpha beta unsaturated case, right? So if the alpha beta unsaturation is present next to the carbonyl group, so if there is a heteroatom containing lone pair or a double bond, and that can basically undergo the resonance and decrease the double bond character of your CO, or increase the single bond character of your carbonyl group, then corresponding stretching frequency value is basically decreased. So these are just a very typical questions. Even they will not ask you in the exam like MCQ, or MCQ they can ask you regarding a trend, that's it. like this whatever values that we have discussed, they can just give you some compound and ask you to arrange in decreasing or increasing order of stretching frequency. But in interview they will just if you prepare for this topic or for organic mostly, or even in the physical chemistry, they can just ask you like what are the spectroscopies, most the common like mostly question will ask from this topic, right everyone? Because basically whenever you will do chemistry in lab, you have to finally analyze your molecule, you need the data for like how you are determining your structure. So that time these are the very very minute part, like minute informations, they can just ask you question on that. Okay, so understood this? Any doubt here?
Understood, ma'am.
Okay, so basically we see the order: acid chloride or fluoride greater than anhydride greater than ester greater than your aldehyde or a ketone greater than your carboxylic acid greater than amide. Okay, so this is basically the general trend that we observe in the value of stretching frequency in case of the compounds containing carbonyl group. Okay, so yeah, just mark it important. And whenever you will revise the chapter, just go through this chart once. Okay, then like after you see for 2 3 times, mostly you will able to memorize like in what range the compound stretching frequency is coming. Okay, and yeah, so as we discuss here, just one more point, like the positive charge on oxygen can lead to the minus I effect, inductive effect, increase in inductive effect, and hence its touching frequency value will be high. Okay, so that's also remember, if in carbonyl group if there is a positive charge coming on your oxygen, which means the inductive effect of oxygen will increase, right? And hence the touching frequency value will also going to be high. And these are some like mostly these values are like very few time the question come from this, but it's like if you able to remember, just remember it like if there is an Rn3 group, then the corresponding stretching frequency will come in the region of 2150 centimeter inverse. If there is ketene like structure, but we replaced carbon with nitrogen here, then the value will come around 2270 centimeter inverse. If we replace oxygen with sulfur, the value will come in the region of 21-25 centimeters. So only once or twice, I think one or two questions in PYQ are related to these values. So it's not mandatory, but if you are able to remember after revision of all chapters, just remember this some value. Okay, so in nitride group, the value will be around 2150. In case of isocyanate groups, the value will be in the region of 2270. And in case of this isothiocyanate group, the value will come in the region of 21-25 centimeter inverse. Okay, okay. And like this question also, like why the ester is having the higher value than aldehyde and ketone. Okay, so just be clear with this concept. If you have any doubt, just ask me now. Okay, because these are very like these are very minute information, and they will mostly ask question from here if they are going to ask the question on spectroscopy. And if you prepare for the IR topic or UV topic, these are the most famous question they will ask for most of the students. Okay, so just be clear with these small concepts. So as we discussed here, just note that if your group is basically electron withdrawing in nature or having some kind of minus I effect, then your stretching frequency value will increase. G group means I am talking about this group. Okay, the group which is next to your carbonyl carbon. And if this group is electron donating in nature or having plus I effect or plus M resonance effect, in that case your stretching frequency value will decrease, because in that case this carbon will be like its electrophilicity will decrease, right? So everything is getting played on the basis of the electrophilicity of this carbon. So if the electrophilicity of this carbon is increased, means the double bond character is higher, or it will be the bond strength will be higher, and corresponding stretching frequency will give you a high value. If there is an electron donating group, then the electrophilicity of this carbon will decrease, and because of that the corresponding C double bond of bond strength will decreases, and hence stretching frequency will also decrease. Okay, so these are some short notes for this IR stretching frequencies and corresponding bonds. Okay, now if let's discuss some other point, like short points in IR spectra. So when we are talking about alcohol and phenols, remember that if there is a free OH present in a molecule, then you will get very sharp and weak, means I'm talking about intensity. So if your IR spectra is like this and you are having a free OH, then you will observe like this kind of spectra. Okay, and for example this is something around 3600. So if you are having a free OH which is not undergoing any kind of hydrogen bond, in that case particularly you will get a sharp peak, and the intensity will be weak. Whereas in general, if there is a hydrogen bonding present, then you will get, and as we discussed, it can be intramolecular hydrogen bonding or it can be intermolecular hydrogen bonding. So we know that, right? Intramolecular hydrogen bonding is going to like it's not depend on the concentration, so the effect will be much more higher or stronger. Hydrogen bonding effect will be on stretching frequency, and hence value will be in the region of 3200 to 3300. Whereas intermolecular hydrogen bonding, we can regulate it by using the concentration or varying the concentration of your solution, and hence its value will lie in the region of 3300 to 3400 centimeter inverse. Okay, so remember here the stretching frequency of intramolecular hydrogen bond is always going to be less than the intermolecular hydrogen bonding. Okay, so here what I was talking, that if there is a free OH, means there is no hydrogen bonding, or if we able to make, actually if there is OH there will be hydrogen bonding practically, intramolecular or intermolecular hydrogen bonding will be there. But if we able to keep it in a vacuum in a such a way that if there is a free OH group present in a molecule without any hydrogen bonding, it will give you a sharp and the weak intensity signal. Otherwise mostly you will observe such kind of broad peak in the region of around 3200 to 3400 if there is a hydrogen bonding present in the molecule. Okay, then you will observe a broad peak in your stretching like the IR spectra. Now and if we this is about the OH stretching frequency. Now when we are talking about the CO stretching frequency in the compound, like so in CO stretching frequency in your alcohol or a phenol molecule. So in case of alcohol, the stretching frequency will be in the region of 1100 centimeter inverse, whereas in case of a phenol it will be around 1200 centimeter inverse. Okay, because of there will be the double bond character here, right? So the carbon we are, whatever carbon we are considering is sp2 hybridized, right? Whereas in alcohol that will be sp3 hybridized. So that's why there will be a like minute but on the basis of this we can't actually the peaks are so much overlapping. So when you will see the actual IR spectra, like when you see it first time, you are not able to guess like what kind of structure and the functional groups are present. But with the habit of it, and as much as you go through like many spectra, then you are able to, like, you will get the skill that yeah, we can now able to guess like what kind of functional group are present, or we can determine what functional groups are present in your molecule. Okay. Okay, so now next, this is about the OH, right? Now we will talk about NH stretching. So in case of NH stretching, there can be a primary amine, or there can be a secondary tertiary amine can be also present, right? So in case of primary amine, it's NH2. So as we discussed, there will be the similar atoms, but we will get a 2 NH peaks, and that mostly comes in the region of 1350 to, oh sorry, that is around that is C double bond NH2 peak, right? That is nitro peak, sorry, I'm confused between the values. So NH2 peaks will be broader, so that will come in the region of 3300 to 3400. So this is basically your symmetric stretching and asymmetric stretching peaks will come. And again, in case of primary amine, it will be NH, right? There R groups will be attached, alkyl or other chain side chains will be attached. So here corresponding only one NH peak will be present. So between primary and secondary amine, you can distinguish based on the number of peaks you are getting. If there are more than one similar atom, like here in primary amine 2 hydrogens were there, so you will observe the 2 peaks. One is around 3300 and other is around 3400, or in that region particularly. But in case of secondary amine, you will observe only one peak around 3100 to 3500. In that range you will observe only one peak. Here you will observe the 2 peaks. Okay, so there are 2 peaks you will observe. In this case only one peak in this particular region you will observe. Now you can ask they can also ask you a question, or you should have a doubt here, right? Because like in case of OH, the range is also in the somewhere around 3300 to 3600, or in even in case of NH, in case of amine, it is also overlapping in that range, right? Around 3000 to 3400 or something. So how basically we can differentiate between the NH peak and the OH peak? So just difference between this is that the OH peaks are mostly the broader in nature, and whereas NH peaks are almost a sharper in nature. Okay, so that's the only small difference by which you can vary between like you can distinguish between these two functional groups. Because even like whatever kind of OH is present, either it is a free OH or intramolecular or intermolecular, it's basically giving the range or lying in the range of 3100 to 3600. 3600 is possible only when there is no any kind of hydrogen bonding is present. And mostly in case of NH, it also lying in the region of 3100 to 3400. So basically these both regions are overlapping with one another, but just by nature of graph, that is the in case of OH, because of a hydrogen bonding, your graph will be much more broader, not just because of hydrogen bonding. In case of NH also hydrogen bonding is possible, but what basically happen, see here, the electronegativity of oxygen is greater than nitrogen, right? So, or in other word, this hydrogen is highly acidic in character compared to the NH hydrogen, right? So, there will be a fast proton exchange happen in your molecule. So, it basically appeared like many OH groups are present. Okay, so why basically you are getting that much broader peak? I show you like one schematic here, right? If there is free hydrogen, the graph will be very much narrower, but if there are hydrogen bonding present in a molecule, you will get that much very broad peak. So why basically what's the basic idea why you are getting that much broad peak is basically we just, it feels like even there are only 2 or 3 molecules, it just appear like there are in a system there are multiple hydroxyl group present because of the proton hopping mechanism. Okay, so this hydrogen is highly acidic, and it's having a high because of higher electronegativity, it just basically appear like this proton is basically hopping here. Then further, if there is other OH molecule in a system, this hydrogen is hopping here, this hydrogen is hopping here. So it basically because of the proton hopping is basically taking place. It appear like proton hopping is happening, or it just looks like there is a some growthous conductance is happening in the molecule because of this proton hopping, and that's why it appeared like there are multiple hydroxyl group present in a molecule, and hence this peak, corresponding peak you will observe will be the much more broader in your IR spectra. Okay, so that's the result of this uh, growthous conductance or proton hopping. So in this way you can basically differentiate between the OH and the NH functional groups. So this is understood whatever we have discussed, alcohol phenol and the difference between OH and your NH stretching. Any doubt here?
Ma'am, in the graph, what does the intensity represent?
What? Can you repeat?
In the graph, like if intensity is more, is it like
Yeah.
corresponding to
So
like,
it's basically representing like the concentration or the number of molecule. For example, even we'll discuss in NMR also, right? So there is one part like integration is there, like how many numbers are present and the intensity is there, right? So intensity of your graph is basically, for example, this is one and this is the another. So and this is the third one. So basically this intensity is representing the number of the same bond that are present in a molecule. For example, there are multiple NH bond present in a molecule. Okay, so in that case it means that the corresponding electric field component, for example this electric field component is around 2 tesla. So this 2 tesla is generated by the for example 1000 such a NH bonds. Then it means when this corresponding particular another compound we are taking and there are less number of NH bonds present in that molecule, then for example there are 500, okay, 500 such molecules are present, then the 2 tesla are generated by the less number of molecule, which can basically give the resonance with your IR electric field, right? So that is basically, so basically it's representing how many number of bonds are present in the molecule or concentration of that particular solution. Understood?
yes, ma'am.
Okay, so we'll discuss this again in NMR, maybe it will be more clear, but yeah, in IR it basically represents you the how many number of such bonds are present. Okay.
While testing, will there be like a fixed concentration?
While testing, yeah, there will be a fix, like there
Do
will
they
be a,
always take like fixed
yeah,
concentration?
there will be a cuvette here, right? So for example you have some molecule which is having, for example this is NH2 is there, right? And this is amine molecule. For example this is the glass cuvette or a quartz cuvette that you will use for IR spectroscopy, and certain amount like the particular critical amount was taken for testing the solution. But for example in that particular concentration whatever compound is there, it is not this simple molecule, there will be a complex some natural compound will be there, or some other chemical structures will be there which will be having a multiple bonds there will be, right? Not only the NH2 group will be there, there will be some carbonyl group or ether linkages, or general your unsaturated or saturated chains will be, long chains will be there, right? So in that overall what we say, overall constituent present in your chemical structure, particularly that stretching frequency or that particular bond is contributing how much, based on that this particular intensity ratio you will get. Okay.
Yes, ma'am.
Yeah. So if you are taking the similar kind of compound but which is contributing a less contribution toward this electric field component, which is resonating with your IR radiation, then corresponding intensity ratio will be lower.
Yes, ma'am.
Okay, so now we'll move forward toward the like there will be some terms in IR spectroscopy, general terms. So the first one is called your fundamental vibration or the absorption. So basically the fundamental vibration is arises from excitation from ground state to lowest excited state. So the GS means ground state, ES means the excited state. Okay, and mostly the peak correspond to this fundamental vibration will be having the highest intensity. So intensity will be the highest for the fundamental vibration. So for example, um, this is your ground state and this is your excited, this is the first excited state. There will be more multiple excited state present here. So whenever there will be a radiation in your molecule, if from your S is equal to 0 to S is equal to 1, this is electronic levels. So from your ground state to the lowest energy excited state, if the excitation is happening, and the corresponding peak that you will observe in IR spectra is called the fundamental vibration, and usually this will be having the highest intensity. Why? Because always see that whenever you are going to talk about S1 to S2 or S2 to S3, it depend upon the population, right? So here the population at ground state will be always highest initially. So that's why whenever radiation is going to happen from S0 to S1, the probability will be higher for the excitation. So that's why it's going to give you the highest intensity. Okay, so this vibration is called as basically your fundamental vibration. So in IR spectra is basically there will be multiple peaks will be present, like overtone, combination, difference band, and this fundamental vibration, etc. But the highest intensity the corresponding peak related to highest intensity will be always a fundamental vibration. Okay, then the second term is called the overtone. So what are the overtone? This is basically we are doing the excitation from ground state to higher energy excited state, then corresponding integral multiple of the fundamental frequency band you will get, then corresponding frequency whatever you will get, and the corresponding band or the spectra intensity you will observe is called as your overtone. Okay, and usually the overtone intensity will be less than your fundamental vibration. So this is because of the energy gap. So always it's easy to access, like molecule will access first the lowest excited state, right? So try to access where the energy compensation will be the less. So that's why the fundamental vibration will be always having the higher intensity, or the higher intensity, and corresponding overtones will be having the less intensity of it. Okay, so if your fundamental vibration is at particular nu bar, then your overtones will be having integral multiples of that fundamental vibrations. Okay, so this is representing the wavelength, don't confuse, this is basically representing a wavelength. So energy wise or frequency wise, always remember that the fundamental vibration is always greater than your overtone, and this is basically representing your wavelength. Okay, wavelength at which these excitations are going to happen. So this integral multiple means this is related to a wavelength, not a frequency. So that's the idea. So if we represent it in a diagram, if this is the first vibrational level, second vibration, like higher excited state vibrational level, then this is your fundamental vibration. These are your overtone, okay? And there is one more term called as hot bands. So if the excitation is taking place or excitation arises from higher excited state, then that is called as a hot band. Means what? For example, if the excitation is starting from V1 to V2, this higher excited state, then that is called as hot band. So here you will, after basically whenever there is a fundamental transition is happening, some molecule will be remain in the excited state, right? And that excited molecule, if the probability will be less, but if they are undergoing excitation to more higher excited state from V1, then that is called as the corresponding band you will get in IR spectra, that called as a hot band. Okay, so you understood what is fundamental vibration, overtone, and the hot band.
Yes, ma'am.
Okay, now when we are talking about IR spectra, there will be some kind of couple interaction can also happen. So couple interactions are basically what is happening. More than one vibrations are excited by absorption of single photon. So more than one vibrations were excited by absorption of a single photon. So you are basically providing a less energy, but corresponding to that energy, more than one vibrations were happening. Then the such kind of interaction is called as your coupled interaction. So there are two types. One is called as combination band, and other is called as your difference band. So combination band is basically the sum of two band that is undergoing the vibration due to the absorption of single photon. So it's given by the combination band frequency is nu1 plus nu2. These are the two bands that undergoing a vibration. And in case of difference band, some energy will be, the corresponding vibration happening is basically uh, difference of the frequency, or what we can say, the wavelength corresponding to these two particular band. If such kind of vibration which is intermediate between these two, or difference between these two is happening, then that is called as the difference band. Okay, so this is the some coupled interaction along with your primary interaction can happen, then such interactions called as your coupled interaction. Okay, and we discussed about the Fermi resonance, right? So basically this Fermi resonance in aldehyde compound is actually the example of this coupled interaction. Okay, so what is basically happening? In Fermi resonance you will observe basically such kind of duplet in the region of 2700 to 2900 centimeter inverse. So this doublet is basically observed. So it basically result between fundamental stretching vibration get coupled with it get coupled with first overtone bending vibration. So when your fundamental stretching vibration coupled with your first overtone bending vibration of your CH bond, so fundamental vibration of this CO stretching, it get coupled with your first overtone bending vibration of this CH bond, this CH bond. In that, if they are coupling together, that interaction basically give rise to this doublet. Okay, and that is called as your Fermi resonance. So Fermi resonance is actually basically result of this coupled interaction. Okay, understood?
Yes, ma'am.
Okay, so this is all about your IR stretching frequency, like whatever point we have discussed. This is the introduction and concepts that we are going to use. So we will solve some examples through which we can understand this principle. Okay, so let's solve some examples, and these are also some, like when solving you will get some short keys how to solve or how to approach the MCQ. So we'll solve now. I'll solve some example and I'll give some for homework or something. Okay, so 1 minute. It's coming like this. If there is benzaldehyde molecule, so you have to determine like this order of stretching frequency. Okay, so order of stretching frequency you have to determine. So can you try to solve it?
Ma'am, C greater than E greater than B.
C greater than,
E greater than B.
your voice is breaking. Can you pardon?
E
C greater than. B, right? So we uh, we already discussed, right? So whatever G group nature is present, based on that we can determine. So we know that if your G group is electron withdrawing group in nature, in that case your C double bond character will increase, right? So we can see that here this is a nitro group, means strong electron withdrawing group. So with this the force constant will increase, the stretching frequency will increase. If we see here, the OMe group have a two lone pair, so it can just donate the electron. So that's why it basically increasing electron density on your this carbon or overall benzene ring. So it's basically showing you the plus I effect. So that's why corresponding stretching frequency will decrease. But whereas here there is no any corresponding group is present, so compared to B, A will be having the higher stretching frequency. So your order will be C greater than A greater than B. Understood?
Yes, ma'am.
Yes, ma'am.
Yeah. So I'll just write a formula for a reference. Stretching frequency is basically 1 upon 2 pi C into root of K by mu. So just like whatever factor you are considering, just see that how it's affecting the force constant and reduced mass. Based on that we can just determine the order. Okay. Now write the second question. If we consider the cyclohexanone versus alpha beta unsaturated cyclohexanone, then which will be having a higher stretching frequency here?
Cyclohexane.
Yeah, so cyclohexanone will be higher, we discussed, right? So this will decrease the double bond character, or increase the single bond character, and hence corresponding stretching frequency will be decreased, right? Then the next one is acid chloride, acid fluoride, anhydride, ester, and amide. So now, like, what will be the order? What will be the order here?
BACDE.
Yeah, correct. So that will be B greater than A greater than C greater than D greater than E, right? So here just minus I effect will be there. We already discussed here also minus I effect. So that's why, and we discuss the range also, right? So this will be around 1870. This will be around your 1800. Acid anhydride will be around 1760 to 1780 centimeter inverse. Your esters will be around 1735 to 1715 centimeter inverse, and amide will be around 1660 to 1680, right? So in this way, like just revise the values, because that will help you not now only, but even when you will continue as in labs or something, when you will analyze the compound, it will that will help you. Okay. So for carbonyl compound at least you should know the values. Okay. Yeah. So this will be your answer, right? Yeah. Now let's discuss the next question.
C, B, and D.
Can you repeat?
C will be the greatest, and then B and A.
Yeah, correct. So order will be this, right? So how you solve? For example, when you are considering here, we have to consider how the electrophilicity of your carbonyl group, electrophilicity of carbon and carbonyl group getting affected, right? So when you are seeing here, this alpha beta unsaturated is there, as well as this lone pair can also undergo the resonance. So let us consider that if this is 100% electron donation, this is also donating. So just for our easy approach, we can just say that there is 200% electron density increasing in the pi star of this C double bond O. When we are talking here, here there will be only the resonance effect present, right? So let's consider it as 100% electron density is going into the pi star of this empty pi star will be there, right? So this is pi star of your C double bond O. In that, basically 100% electron density population is increasing, whereas here you can see that this electron density can either undergo the conjugation with this double bond, or either it can undergo conjugation with the C double bond O. So means the 50% is going toward the double bond and 50% is going to the pi star of this carbonyl group, right? So the basic principle here to highlight is, as the electron density in pi star orbital of C double bond O will increase, then the corresponding stretching frequency will decrease. So they are inversely proportional to each other, okay? So this is important one. So basically you can remember it or apply the concept like this, or just the electrophilicity, that both are actually the same concept. So when the electron density is going toward the carbonyl group, the corresponding carbon electrophilicity is getting reduced, right? So based on that principle, you can just mark it as C greater than B greater than A. Clear, right?
Yes, ma'am.
Okay. So the next question will be, it's on the same principle. So see here, similar to that, right? So here there will be 50-50% sharing. Here it will be 100% electron density, not 100, 200%. Pi bond is also there, right? So that can also donate. Here only 100% electron sharing is happening. So your order will be A greater than, the stretching frequency order will be A greater than C greater than B. Correct? You're understanding,
Yes, ma'am.
right?
Yes,
Yeah,
ma'am.
okay. Okay, then solve the next question. There is oxygen here. A, B, and C. Can you solve this question?
B greater than A greater than C.
Yeah, correct. So B greater than, A greater than C. So now you understood, right? So here there will be the 100% electron density in pi star will get shared, here there will be 50-50% sharing, whereas here there will be 200. Like even here there is 50%, but from this way it's also increasing electron density in pi star, so it will be 200% or to 150%. So that's why the order will be B greater than A greater than C. Okay, so the next question is how to determine the stretching frequency order of phenyl acetate, para nitrophenyl acetate, and the methyl benzoate. So yeah, so sometimes MCQ they won't directly give you the structure, but they will give you the IUPAC nomenclature. So you should able to draw the structure, right? So how the phenyl, you know, right? In whenever we are talking about the ester, we basically called it as alkyl alkanoate. Okay, so nomenclature will be alkyl alkanoate. So similarly, phenyl acetate, it means that next to oxygen the pH group is present there, right? My structure is bad, but yeah. And acetate group is there, means that will be C double bond O CH3. So this will be your phenyl acetate, right? Then para nitrophenyl acetate structure, how it will look? CH3 C double bond O attached to your phenyl group, and at para position it is having a nitro group. And the third one is methyl benzoate. So now this is attached to C double bond O OCH3. Okay, so this is ABC. Now determine the order. What will be the order?
CAB.
What? C. Can you pardon?
CAB.
You are saying C first or B? I didn't get. Okay,
C
so
first, I think.
no, C won't come first. See, there will be. Okay, we'll see, discuss. So see here the electron donation will happen on both sides. This is basically sp2 hybridized structure, right? So there is double bond here also. So here the sharing will be 50%. Now here see that there is an electron withdrawing group present. So most of the electron density can be also it it get attracted toward this nitrophenyl group, because nitro is much more strong electron withdrawing group, right? So the electrophilicity of this carbon is more as compared to this one, and here you can see that this OCH3 is basically giving you the plus I effect, right? And this whole group, like the CH3 group, is basically giving you the plus I effect. So again here the electron density in pi star will be the 100%. So now and here the electron withdrawing group is present, so because of that the sharing will be, we can consider it as also 50% sharing is happening. But because of electron withdrawing nature, this carbon is more electrophilic compared to the first one. So your order will be, the stretching frequency of B will be greater than A greater than C. That's what you are saying.
No, ma'am. I got confused.
Okay, okay. So now you understood how we are applying it.
Yes, ma'am.
Yes, this is a pi star. Just see, like, as I told you, na, like, see the G group. What is next to your C double bond O? Either it's electron withdrawing, electron donating. If it's electron donating, means it is a last. Like, it's having stretching frequency very less. Okay. So just focus on how the electrophilicity of this carbonyl group is getting affected. You understood the concept,
Yes.
right? Any confusion is there?
No, ma'am.
Okay. So I'll take two example and then we'll stop. Next is your CH3 C double bond O C2H5 versus CH3 C double bond O. So when you're comparing this, yeah, now tell me between A and B, which is having the highest stretching frequency.
B.
Yeah, correct. So now you understood, right? So here again, there will be, if there is OR group, then you know that it will show the plus M effect, right? The electron plus M effect or the plus I effect it will show. So the lone pair of nitrogen will get donated to your carbonyl carbon. So therefore again here electro